So I showed you just this monotonic calibration. We also have the classical ones, for example, R2-3, which are known to have two branches, one for the low metallicity and one for high metallicity. And in that way, we built over 21 calibrations, which were already reported in the literature, and we found 6 new ones. So a lot of indices that have been explored in the literature. These are the new ones, which are based on argon, neon, oxygen and helium, argon and nitrogen and sulfur. And this one I have to note because I'm going to explain something about it. But we found these regions as well. We also calculate the dispersion of how they differ. We compare, we take spectra of one of them. We calculate the value of the metallicity using the calibration and the real direct value. And here you can see some difference. For example, for the N2 calibration, it behaves relatively well in a very good range, but it diverges for the high metallicity ends. In some cases, for example, the O3 N2, it works relatively well for high metallicity, but then not very well for low metallicities. And this one as well, with different dispersions in each of them. And if you have two branches, metallicity with two branches, well, in some cases they behave well for the low metallicity one, but not very well for the high metallicity, and they are completely wrong for some branches. So depends what you want to do and which lines you have available in your spectra. And also, one of the things that you should consider is not using only one or rely on only one calibrator, but use different calibrators to see if they somehow agree. We also compare our calibrations with literature data. And for the most famous one, there are a lot of calibrations and papers. How you can see that the shades in gray in the background are the locus of the sample. And then, well, we have the yellow lines are calibrations, and then in the middle, many calibrations depending on the reference. And here, this rectangle shows the validity range of a certain calibration in the literature. So for most of the cases, our data, our calibrations, have the longest range for a given index. Not in all cases, but for example, this one, this yellow one, it was produced using only photoionization models, and well, it is completely wrong in terms of the offset, but also in the range of the observable regions that can actually be observed in the universe. But then, with not very well-known indices, things are strange. We found this calibration, which is completely off of the data, and in some cases, well, the validity range of some other calibrations are very reduced compared to the calibration that we are now proposing. And coming back to the high redshift metallicity calibrations, where I mean, a lot of work is done in the last years, because we are looking at really nice spectra of James Webb. But they construct the calibrations using relatively few regions, and in this way that is, as I told you, upside down. So this is our two calibrations that were actually published while I was doing my calibration. That's why instead of 6 new ones, I only have 4 new ones. But anyway, I'm going to show you that it doesn't matter. So these are based on argon-3 and neon-3. But if you put these calibrations by Sanders and their collaboration and compare to our data in the other way, well, you see that this is actually the range that they cover in the index, which has nothing to do if you take the data, the full data, the full sample. And another thing that is in discussion in the literature is whether these calibrations, or do we need other sub-calibrations for the high redshift universe, considering that the spectra, the ionization parameters, the conditions, the excitation are supposed to be different from the local universe. But we think that this is not the case, because, for example, in this case, well, the objects that they found fall in where we have most of our regions in the local universe. So there's actually no shape or no offset from the local calibration that we can derive. And also the numbers are important to differentiate. For example, in this case, they only have 48 regions for this calibration, while we have over than 1,800, 300 regions, and also in this case. So in this case, numbers are important. So this is just what I mentioned, that the special calibrations in the high-redshift universe are only built mostly in these regions where we have most of our data in the local universe. So something that we're going to explore is whether we really need calibration for high-redshift objects, or the ones that we are considering for the local universe also work. And this is another example for R3. This is just one that I'm going to skip this way. And also have fairly strong line indices. We explored many indices, and we found that in some cases there is no strong correlation or correlation at all. But we also found that for some indices, there are actually calibrations that are published for this calibration. For example, this one, where, well, you have this calibration here, that is nonsense, of this calibration here, no? Which is, again, because they have very few objects in the high-redshift universe, and, well, you have something to publish in the web, but you publish it. Okay, but for that, we are also doing the same thing, but now compiling high-redshift objects. So Omar is my student at INAOE, the master student. He's compiling over 100 high-redshift objects with aurora lines measured with the James Webb. And we are in the process of putting them into the format of the desired sample, and we're also going to include these over 100 regions, high redshift regions, up to redshift 10 into the new sample, and see how things proceed. And we're also going to considering to compare our calibrations with models. So this is a model by Christophe Morisset in Mexico, in which this is exactly the same calibration, and this is based just on models, over 3 billion models of star-forming region that they have in the database, and it is color-coded in terms of the ratio of nitrogen to oxygen. So this is one of the reasons, of the top reasons that this dispersion of the calibration, well, the reason of the dispersion. But with the desired data, we can actually measure this ratio, and we have something like here. So it's something that we are going to work also closely with the people doing models to understand if what they find in the models, the dispersion that they find in the models, also is reproduced in our data. But for me, when I saw this plot and how well it's closely resembled the real data, it was really nice. And still we have so many things to do. We're also going to analyze how the ionization parameter, for example, just the ratio of in terms of the ratio of the oxygen emission ions changes with respect to the index and to the metallicity, and we have many other problems that we need to understand. For example, what is the impact of the diffuse ionized gas? We need to add a correction for the nitrogen over oxygen ratio. There's a blending also for high metallicity objects, in which you can also find one iron line at the same wavelength, or the 4363 line, overlaid features, multi-component analysis, etc. And also, for example, there is something that is, well, this was my PhD student, who is now a postdoc at Granada. He did a really nice work on the impact of the diffuse ionized gas. I have another PhD student which is using a sample, or well, in this case, Raul only worked with 8 galaxies for news, and now Fernando is using over 200 really nice quality Funk type galaxies of news in order to also derive properties of H2 regions and the diffuse ionized gas, and see the impact of this into the calibrations. And many things to do. So these are my conclusions. We are presenting you a new generation of 27 strong line calibrations using the largest database with Aurora lines for the desired sample. These are homogeneous data with strict quality control and very robust statistics. These are the first calibration which consider both homogeneous and inhomogeneous temperature determinations. We extend the validity range for most of the calibrations from the literature, and we think that we do not need special calibrations for high redshift objects, but something work in progress. And this hopefully will provide a strong framework for the study of chemical evolution across time. And please, if you observe galaxies or spectra with auroral lines, please work it with errors. Thank you very much.
Fabian, questions for Fabian?
Where does this data come from this desire? Where does this data come from?
From 225 publications.
But how many telescopes?
Hundreds. Well, probably not hundreds, but dozens of telescopes. I mean, we have publications from, as you can see in the histogram.
But I mean, are they long sleeves or IQ or like
everything? Everything that you can find aurora lines, which we could have, well, aurora lines to determine temperature and lines to measure the density. So you have regions from the 1979 to today.
But you're not worried about possible problems, like you have different instruments, different telescopes, different calibrations.
I'm not worried, I'm concerned.
Because even when you work with metallicity gradients, exactly for the same galaxy, you get a gradient if you use Muse data, and you get a different gradient if you use some data, for instance. So you have a difference, a considerable difference in metallicity. Using the same method, just changing the instrument. So I don't know how is that affecting your data.
Well, you when you see the dispersion here, any of the dispersion, we have to understand why. If there is an intrinsic dispersion because of the physics of we are measuring the things wrongly. For example, you are right. I mean, if you, and that's why we didn't consider H2 regions from the Milky Way galaxy, because we have aperture problems. So we were just measuring like the very hot regions, the very hot sun of the H2 regions. And if you even take, for example, Orion, well, I'm going to skip that because I'm going to take it to other place. But yes, I mean, there's a lot of issues, but if you really want to do this right, you have to go and observe these 2,000 regions with exactly the same telescope, with exactly the same spectrograph, and that's at this point somehow impossible now. So this is how things were done in the past. And what we are proposing is just some improvement in terms of statistics and the quality of data. But yeah, I mean, you have many sort of regions and many sort of how the spectra was observed in different ways, with different instruments, with different techniques, different detectors.
So how is the ionization parameter affecting your calibrations?
Yeah. There you go. This is color coding in terms of the ionization parameter based on oxygen lines. So you have some sort of effect, but not really the dispersion. I mean, it's something that you expect, this trend.
But can you give us a calibration that is sort of less affected or corrected somehow by the ionization parameter? Because those are the type of calibrations
Yes.
I like to use.
This is what. This is paper 2. Yeah. Actually, Enrique Perez Montero did something like that for M2. So, I mean, here you can see some effect of the nitrogen or oxygen ratio. But I mean, it's not that clear. I mean, for a given index, you can have several values, no? So we'll see how it works.
It's just about the evolution, or presumably evolution. Are you because right now what the calibration you use for high redshift data are the local ones. So are you expecting these calibrations to change?
Personally, not. But they argue that they should be different because the physical conditions of high redshift first galaxy are different from the local images. But it's something on the discussion.
Because that's just physics. Are you expecting them to change? You can apply some extreme physics or some type for high redshift galaxies for the calibration itself. I don't know.
That's exactly my point. I mean,
it's also like the garbage that you were talking about, like that the other plot with the arrow. That's just a cloud.
It's very far away, but anyway. Yeah. I mean, as I showed you, I mean, there are like over 6 publications in the last year of high redshift metallicity calibrations using just few regions in the district data. Yeah. I agree.
Fabian, I understood that you included in your sample a few galaxies at Z about 3, is that correct?
Yeah.
And they were in the middle of the different plots with average values. Why did you decide to include such a small amount of objects at a given redshift? I mean, what do they contribute with?
Because our principle is that we include every region with auroral lines which fulfill our selection criteria.
No matter the redshift?
No matter the redshift and no matter anything else. So for example, the high redshift objects, they fall, well, where they are finding the high redshift objects in 1/10 metallicity, something like that. These are the squares that you see here. So we have low metallicity regions, like these ones, but also almost
But something that worries me is that in terms of completeness, they could be introducing some biases, no?
Yeah, sure. Yeah. Oh, you mean these objects or the authors that are just proposing the new calibrations?
No. The equal 3 objects.
Why? Because, I mean,
well, for sure they're going to be bright. So
in this version, we have, for example, let me go here.
Stellar masses are going to be higher for sure. Because at Z equal 3, they are going to be like numbered galaxies, are they? Aren't they?
A redshift 3.
Sure.
Yeah.
So I would expect them to be high stellar mass.
Yeah.
So they are completely different galaxies. It's a completely different universe.
But that comes from, from the to the point of Maritza. When you do the mass metallicity relation, you have, I don't know, thousands of regions, millions of regions. But what is the fiber of the Sloan sampling?
Sure.
So it's basically the nucleus of the galaxy. Depending on the redshift, you are going to sample the nucleus or the whole galaxy. So if you sample the whole galaxy, you have like somehow surface brightness weighted abundance, no? Which should be like the mean metallicity of the galaxy. If you're just sampling the nucleus, you're going to get a higher metallicity. Yeah, but in order to do it right, we have to do what I just mentioned, like to observe all these regions with the same instrument, with the same telescope, and with the same apertures and with the same criteria, which is impossible. There's also there are problems, of course, but it's the best we can do.
Well, from the top of my head, I'm thinking that, for example, the MOSDEF survey, which was done with MOSFI at Keck, they by themselves, they have several hundred galaxies with whole emission lines and so on.
Yeah, they're included here.
They are included.
Yeah. Yeah, Cesar and Jorge and Eduardo and myself, we are always looking at all the references which we can all this data.
ABS entry that says
Metallicity, Aurora, goes into it.
Can you check whether is there any question?
Are there any questions online? I was wondering what kind of temperature distribution are you using in the low redshift and high redshift sample? Is it the same? Or?
The temperature,
Sí.
well, you can see here, for example, for the low metallicity galaxies, you have 20,000 Kelvin, and for the high metallicity, well, I don't remember the lowest metallicity, but it should be around 3,000 to 4,000 Kelvin. So the maximum value, I remember, is 25,000. It doesn't get to 25,000, like 23,000.
It doesn't affect that much the fact that you use homogeneous or not homogeneous.
Well, the difference is this offset. So the homogeneous case and on an inhomogeneous case is basically a 0.2x shift in difference.
And in one of the last slides, when you mentioned multi-component analysis, do you have an ionized outflow in your sample that you have to remove to derive?
But the point is that we don't have the spectra. We only take the tables from the publications.
Okay.
So again, if you want to do it right, then you will have to share all the data and then separate the components and then do it. But these are like 10 PhD theses.
Yeah.
Any other questions?
No.
Yes. So in that table that you are compiling, what information do you add? Do you add like the mass of the galaxy where it's taken? Do you add the sigma of the spectrum if it's published? Or you just keep whatever you need for this?
Again, it depends on the source. I mean, some people give everything,
Then you take everything.
and then we take it. Another they just give H beta and 2 error, and that's it. So.
And I have another question. In the plot when you saw the photoionization models trying to reproduce this change across your sequence, how the N over O is changing is completely different from the one that you get directly from the nitrogen abundance.
Yeah.
How shocked are they?
I don't know.
do they know that it's completely like?
No, I saw this figure because I met Christophe in a conference a month ago in Ensenada. And we met and we discussed this, but we still have to.
Yeah, because theirs is like that and yours is like this.
Yeah, so there's something that we have to do. Well, here there's some mixing.
Yeah, it's true.
Yeah, but here. No, what I was struck for is the shape.
Yeah.
There was like,
wow. There's some different physics.
Yeah. But again, you have to consider depletion of dust.
Oh yeah, sure.
Other features.
And how they correct the stellar absorption in the H beta lines as well, because if you are just relying on the table, so some articles may have done a better job than others, or some others might not even have corrected it. So that's
No, everything is existing corrected data, but corrected by the authors.
yeah.
So we have to rely.
Yeah.
Well, I didn't have to show you, but I mean you have to rely also on the errors of the authors. And some authors talking about this percentage, they quote errors for the aurora lines of 1%. So
there is a human factor.
Can you trust that or not? But again, I mean, you will have to go and observe the object and measure the lines and then get a realistic error.
Well, just ask them for the actual data when you do the measurements.
Well, I don't.
I mean, if you want something really reliable,
It should be repeatable. Yeah. Probably not willing to. Okay, so there are no more questions. Let's thank Fabian.
Thank you.
Perdona porque se me queda frito. Cuando estamos
Thank you for joining us.
pero se queda frito. Se queda dándole frito. No,
ya nada pasó.
vale. Lo que ha pasado, sí se ha retransmitido en YouTube, pero en la que tenía para la semana que viene, porque el número de la clave, la clave va rodando, se ha ido a las. Entonces tengo que coger el vídeo de la presentación.
Sí.
En otro, o sea, tengo 2 vídeos de YouTube, los tengo que sumar y subirlo. Sí, no pasa nada. Así que nada, luego me toca un poquito de video editing para poner
Sí.
en tus condiciones, así si lo quieres mandar a algún colega, colaborador, competidor.
Competidor.
Competidor.